are welcome to the second session under Unit 6. And in this session, you are going to be looking at the reactivity of pyridine. So, at the end of the session, you should be able to compare the reactivity of pyridine with that of benzene. You should be able to describe electrophilic substitution reactions of pyridine. And lastly, you should be able to explain why electrophilic substitution on pyridine ring occurs at carbon number 3. So, quickly, let's kickstart. So, electrophilic substitution reactions of pyridine is the first thing we are going to be looking at. So, in the presence of electron withdrawing nitrogen atom in pyridine makes it to have 3 charged resonance contributors, right? So, these are the resonance structures that can be obtained from pyridine, and out of the 4, 3 are charged. Now, the pyridine ring is therefore electron deficient, implying that the carbon atoms carry a partially positive charge. Right, just as I explained in the previous session, you see, if you look at the resonance structures produced, realize that the carbon atoms are the ones having the positive charge, right? So the carbon atoms are slightly positive charge species. So in terms of reactivity towards an electrophile, which is a positive charge, there's this kind of low reactivity towards it, right? So this means that benzene will be more reactive than pyridine towards an electrophile because of the partially positive charge we see on the carbon atoms. So basically, pyridine is low, has low reactivity towards an electrophile compared to benzene. Okay, so again, pyridine does not undergo Friedel-Crafts alkylation or the acylation process or reaction because of the partially positive charge species that are found on the pyridine ring, right? So the moment the Lewis acid is added to the acid chloride, the Lewis acid quickly accepts lone pair of electrons from the nitrogen atom. So this is what is happening. So it forms a different bond, preventing the acid chloride from attacking the ring. So what it means is this product is never formed. In Friedel-Crafts alkylation, it's not possible. In acylation, it's not possible because the acid reacts with the nitrogen to form an adduct. So please take note of that. Next is to look at the position where an incoming electrophile would go. Now, assuming we activate the ring, which parts of the ring does an incoming substituent, which is an electrophile, go to? So we have our pyridine plus an electrophile. So we can look at attack at carbon number 2. So the nitrogen group becomes our number 1. The next becomes number 2, which is the first carbon. Carbon number 3, 4, 5, 6, right? So at carbon number 2, if you attach our incoming electrophile at carbon number 2, realize that this is the 2 resonance structures we have. And at carbon number 3, these are the resonance structures that we can get. And at carbon number 4, these are the resonance structures we can get. Now, if you look at the attack at carbon number 2 and attack at carbon number 4, realize that there is also a less stable intermediate, right? So we have the nitrogen having a positive charge on it, right? At carbon number 4, you can see the same thing. Now we know that nitrogen is highly electronegative, so we wouldn't want to interfere with positive charges, right? So the moment the nitrogen is positively charged, it becomes less stable. So out of this, realize that all the 3 resonance structures produced at carbon number 3 are all relatively stable, right, compared to the resonance structures obtained at carbon number 2 and carbon number 4. So this means that electrophilic substitution occurs at carbon number 3 because this position produces the most stable carbocation intermediate. Yeah, so please take note of that. Now, this is also a typical reaction of pyridine. So this is bromination of pyridine, and you realize that the bromine group is attached to the carbon number 3, and this is sulfonation reaction, and the bromine, the sulfonic acid, is attached to the carbon number 3. Next is to look at oxidation of pyridine. Now the pyridine ring is resistant to oxidation just as benzene. So what happens is it's the side chains that are easily oxidized in the oxidation reaction between pyridine and oxygen. So in potassium permanganate, it can be used to oxidize the alkyl group here to the carboxylic acid functional group. Similarly, the same thing happens in pyridine. So oxidation reaction of pyridine and benzene are almost always the same. Okay, so next is to quickly look at nucleophilic substitution reactions of pyridine. So just as we talked about, because pyridine is less reactive towards an electrophile than benzene, it means that towards a nucleophile, then pyridine will be more reactive towards a nucleophile than benzene because of the electronegative nitrogen atom that withdraws electrons, the pair of electrons towards itself, right? So in nucleophilic substitution reaction, pyridine is more reactive towards a nucleophile than benzene, and these are some examples. So the next thing to consider is the point of attachment of our incoming substituent, right? Now substitution in pyridine proceeds most readily at the carbon number 2 position, followed by carbon number 3, but never the carbon number. Sorry, followed by carbon number 4 position, but never the carbon number 3. So the incoming nucleophiles readily go to the carbon number 2 position. So you can look at this typical example, right? So we have our bromine being replaced with an amine group, right? And similarly, we have our chlorine being replaced with an amine group. So basically, the attack preference starts with carbon number 2, except the carbon number 2 position is occupied. Then you can think about carbon number 4 position, right? Yeah. So attack at carbon number 2 and 4 produces the most stable carbanion intermediates. So if you look at the resonance structures, realize that the attack at carbon number 2 and 4 will give us the most stable carbanion intermediates. So we can quickly look at the Chichibabin reaction, which is a typical nucleophilic substitution reaction that involves the production of two pyridine derivatives. So we can produce two pyridine derivatives, one with the amine attacking the second carbon and another with the amine attacking the fourth carbon. So in this reaction, you react pyridine with sodium amide to produce these two products, different products. So we can look at the mechanism here. So the incoming amine comes in, and there's the elimination of hydrogen to keep our amine group here, and then finally the removal of another hydrogen through hydrolysis to produce our resulting 2-amino pyridine, right? Now let's look at alkylation of pyridine. Now pyridine can be alkylated with either Grignard reagents or lithium alkylated compounds. So first of all, we can use our normal Grignard reagents that we know to alkylate our pyridine ring to introduce a substituent. So similarly here, two products are formed. You can form the first one, carbon number 2. You can form another one with your alkyl group attached to the carbon number 4. Now if you decide to use a lithium alkylated compound, then what happens is the lithium leaves. Yeah, so let's take note of the reaction conditions. The lithium leaves, and then the alkyl group is attached to our carbon number 2 position. So please let's take note of these two as well. Okay, so next we can also look at the reactions of substituted pyridines. So we've looked at cases where we have our pyridine and we want to synthesize some derivatives of pyridine. However, there are also cases where we can also look at our already substituted pyridine undergoing some kind of reaction. Now, substituted pyridines undergo side chain reactions commonly to the substituted benzene. So similarly, what is happening is this is a typical oxidation reaction where our alkyl group our methyl group is being converted through oxidation to the carboxylic acid functional group. And then also we also have another substituted pyridine group here. So here our ethyl group, right? Ethyl group is being treated with N-bromosuccinimide and then heated to produce our side chain alkyl halide side chain product, right? So to introduce an electrophile at carbon number 4 of pyridine, a pyridine N oxide is used. So all things being equal, whenever you try to bring in an electrophile at the fourth position, what you need to use to scavenge or protect the carbon number 2 position is to use pyridine N oxide, right? So whenever pyridine N oxide is being used, it forces our incoming substituent electrophile to go to carbon number 4 position. So please let's take note of that as well. So we will look at the explanation in this slide. So in order to, just as I said, in order to introduce our electrophile at carbon number 4 position, then the best way is to try and activate the pyridine ring, right? Because the pyridine ring is relatively less reactive towards an electrophile. So the best way is to activate the ring, right? To activate the ring, and you can use hydrogen peroxide in an acidic media to activate the ring and create this intermediate which is very reactive towards electrophiles, right? So then we can introduce our incoming substituent, and the incoming substituent is forced to carbon number 4 position when the pyridine N oxide is being used, because that is what first of all reacts, leaving the ring electron rich, which is able to react with incoming electrophiles that are positively charged.